Hello everyone. So right now I am in my second lecture on redox chemistry. So after discussion of normal hydrogen electrode and followed by electrochemical series, now our next topic is Daniell cell. So Daniell cell is a complete cell. It's a combination of two half cells. Means in one of the half cells there is an electrolytic solution where the cationic metal has been immersed, and in another half cell the same thing has happened. Now what electrolyte or what salt solution has been taken in both the half cells? In the first one, aqueous solution of zinc sulfate has been taken, and the cationic metal, that means the zinc metal, in the form of a rod or an electrode, it has been immersed in that solution. So this is a half cell. As you are well acquainted with the fact that when zinc metal comes into contact with zinc 2+ ions, in that case the zinc metal releases 2 electrons and goes into the solution in the form of zinc 2+ ion here. So this rod or this electrode would accommodate electrons due to releasing of electron by zinc metal. So this would become negatively charged. On the other hand, copper is much below in the electrochemical series, and it has the tendency to attract electrons or to consume electrons in order to become copper metal from copper 2+ ion or the cupric ion. So in this case, in this half cell, a cupric sulfate solution, aqueous solution, has been taken where a copper electrode has been immersed, and copper 2+ ions, after having consumed 2 electrons, that means this rod is supplying those 2 electrons, and consequently this rod has become positively charged. So when these 2 electrodes are connected with each other, and in between if a voltmeter is fit, then it will detect flow of electricity. Electricity will flow from the cathode to anode. That means electrons will go from anode to the cathode. So the direction of electricity is always opposite to that of the flow of the electron. So electricity will go from cathode to the anode, while the electrons would move from anode to cathode. Now in this regard, these solutions, both the solutions would become would lose their electroneutrality, because here zinc plus ions would increase, so sulfate ions would be decreased, so it will be cationically, it will be rich. On the other hand, this solution would be anionically rich. Here the sulfate ions would be much greater in concentration than that of the copper 2+ ions. So these both the solutions are not electrically neutral. So in order to balance this non-neutrality of ions, a salt bridge has been connected. Actually this salt bridge is connecting these 2 half cells. This is nothing but a saturated potassium chloride solution. Okay, so this salt bridge has been symbolized here by double stroke, vertical strokes, and this combination of 2 half cells has been denoted as zinc to zinc sulfate, salt bridge, then copper sulfate to copper. So this is the presentation of a complete Daniell cell, which is actually a combination of 2 half cells. In between there is a salt bridge. Now what about the standard electrode potentials of these 2 half cell reactions? These 2 half cell reactions, in case of zinc it is minus 0.76 volt, and in case of copper it is plus 0.35 volts. So the way of calculating the overall electrode potential of this complete cell is the redox potential or the electrode potential of the cathode minus the electrode potential of the anode. That means the right hand side minus the left hand side. Okay, so electrons would flow from the anode to cathode always. Now this is actually the reverse reaction. This is the reverse reaction of electroplating. Okay, here chemical energy is converted into electrical energy. But during electroplating or electrolysis, what happens? During electrolysis, what happens is electrical energy is converted into chemical energy. So what about the differences in between these two? Let us see. This is the cell reaction where chemical reaction is converted into electrical energy, and here we have put some points here where electrical energy is converted into chemical energy, that is electrolysis. So in the first point, this thing is mentioned, chemical energy to electrical energy, and here electrical energy to chemical energy. Look at the cell reactions. Here zinc becomes zinc 2 plus and copper 2 plus becomes copper. On the other hand, during electrolysis, zinc 2 plus becomes zinc and copper becomes copper 2 plus. That means the reverse reaction takes place. Okay, but the main difference is this is actually a spontaneous process and this is actually a non-spontaneous process where some external potential has to be applied. When this external potential overcomes the redox potential of the two cells, then the reverse reaction takes place. That means the potential of this Daniell cell is 1.1 volt. So for electrolysis we have to apply potential energy which would be more than 1.1 volt. Otherwise the spontaneous process, that means these two reactions would take place. So in order to make them happen in the reversed order, we have to apply electricity having external potential greater than 1.1 volt. Now anode is negatively charged in case of cell reaction, while in case of electrolysis anode is positively charged, and vice versa. That means the cathode is positively charged in case of cell reaction, and in case of electrolysis the cathode is negatively charged. But the fact which is common in both cases, that the movement of electron is always from anode to cathode. Look here, electrons would move from anode to cathode. Here a spontaneous cell reaction takes place. Even if a non-spontaneous electrolytic reaction takes place, then this anode is actually positively charged and this cathode becomes negatively charged. In that case also electron moves from here to here, and anode is always put in the left hand side, the cathode is always put in the right hand side. Okay, so these are the conventions. We have to be very much alert about these things. So where to put the electrodes, the cathode in the left hand side or the anode in the left hand side. Okay, we have to be very much careful about these things. So what about the features? For electrolysis, externally applied potential has to overcome the electrode potential, as I have mentioned here. The minimum voltage is necessary to cause deposition is equal and opposite in sign to the potential between the solution and the electrode. That means, again we move to the previous slide. This is 1.1 volt. So we have to apply minus 1.1 volt external potential. That means here it should be positively charged, it should be negatively charged, and the potential difference should be 1.1 volt or more than that. Otherwise the reverse reaction would not take place. And here the common thing among these two is electrons always move from anode to cathode in both cell reaction and electrolysis. Now both the reactions are the complete reaction complete cell reaction when combined together. These two reactions are actually redox reaction. How? Look here, in the anode, oxidation takes place because zinc releasing 2 electrons. On the other hand, in the cathode, reduction takes place because copper is consuming 2 electrons. So, as a combination of these two, this is called a redox reaction. Redox reaction in case of Daniell cell, as well as in case of electrolysis. Here, during electrolysis, the reverse thing takes place. Here, zinc consumes 2 electrons, so it gets reduced, while copper releases 2 electrons, so it gets oxidized. Now, the Nernst equation. Here, equation 1 is Nernst equation, E equal to E0 plus RT by NF ln A. So, how do we arrive to this Nernst equation? So, this is a cycle. This is a Born-Haber type of cycle. Now, a metal is getting aquated in the form of metal cation. So, this is shown here, a metal, solid metal, and here the metal cation getting aquated by releasing 1 electron in an aqueous medium. So, if this transformation is split into stepwise manner, then these 3 steps are obtained. What are these 3 steps? These 3 steps follow. First of all, sublimation of the solid metal into metal vapor or gaseous metal. So in this regard, the energy required is called the heat of sublimation, because solid to gas is the phenomenon which is known as sublimation, and the heat required due to this is called the heat of sublimation, which is denoted as plus S. This plus sign because heat is being absorbed here or heat is applied here. Next, this metal gas releases 1 electron. So this phenomenon is known as ionization potential or ionization energy. So from metal gas to metal cation, the energy required is known as the ionization energy. Finally, this ion has to be aquated. So this is heat of hydration, but this process has a negative enthalpy. That means it would release some heat, which is denoted as minus H. So we have 3 energy parameters, which is S endothermic, I endothermic, and H exothermic, and the combination of these 3 are actually the overall free energy change of the system, which is denoted here. So delta G is actually a function of heat of sublimation, ionization potential, and heat of hydration. Now we know the equation from thermodynamics, delta G equal to delta G0 plus RT ln 1 by A. Why 1 by A? Because here 1 is the concentration of the solid metal. So for any kind of solid or liquid, the concentration is taken as 1, and A is the concentration or the activity of the metal cation. So that is why it is written as 1 by A, that is product over reactant. Okay. Now if we put delta Z0 as minus NFE0 and delta G as minus NFE in this equation, then we get the relationship minus NFE equal to minus NFE0 plus RT ln 1 by A, and rearranging this equation we get finally arrive to the Nernst equation, E equals to E0 plus RT by NF ln A. Okay, here I must mention that N is the number of electrons which is being released by the metal, F is the Faraday, and E0 is the standard potential, and here E is the normal electrode potential. Now the fact is that during calculation of delta G, we found that delta G is a function of S, I and H. So in case of the transition metals, it is a fact that they have high positive heat of atomization or heat of sublimation and high ionization energy values. So naturally delta G, this is actually equal to plus S plus I minus H, so it becomes less negative. That means the free energy of the system becomes less negative. That means it will lead to non-spontaneity of the change. That means the metals would not like to release the electron readily. So if some question comes to your mind that why the transition metals have low tendency to get ionized, then the answer would be delta G equal to plus S plus I minus H, and transition metals have high positive S and I values, so less negative delta G value, so they have the less tendency to get ionized. The same thing happens in case of the alkali metals and the alkaline earth metals, that means the S block elements. But in the what I say here, in the reverse order it will happen. That means in case of the S block elements, they have very low heat of sublimation. As you know that they are very soft metals, so they can be easily evaporated or vaporized into the vapor form, and they can easily lose their electron, so that they have very low ionization potentials. So since these S and I values are very small, so they have very what I say more negative delta G value here, and as a result they have high tendency to get ionized. So with respect to S and I, if it is explained that the alkali and the alkaline earth metals like lithium, sodium, potassium, why they have the tendency to get ionized so readily, then the answer is that they have very low S value and I values. That means heat of sublimation and very low ionization potential. That means they have more negative delta G values. That means they can spontaneously release an electron. So up to this, that's all for today. The next things will be discussed in my third lecture. Until then, goodbye, have a nice day. Thank you.